Going to, can you use a graphing calculator? Yeah, you can use a graphing calculator. That's fine with me. For your exam, you can use your graphing calculator. And I usually put the equations up there for you too on the board during your exam. I'll probably do that. Just remind me and I'll do that. Okay, so we're going to talk just quickly and finish what we've been doing on the complex ion formation. So we did this in lab today. Like literally we made our complex ions, right? We'll learn how to name those later. But this is what we were doing. We were making complex ions. So when we put one thing, for example, silver chloride, it's insoluble, which now we know really means it's soluble, but just imperceptibly so. Its KSP is 10 to the negative 10th, right? So it's very reactant favored, very small K. But once we add ammonia to it, here's that complex ion that it makes. Now look at the K. And again, KSP because we're talking about solubility, KF because we're talking about the formation of a complex ion, but really these don't really matter, right? Because K is K is K. This much bigger, which means again, that it's a product favored reaction. So that insoluble silver chloride is now soluble. So when we add ammonia or ammonium hydroxide to the solution, the silver chloride increases the solubility of silver ions, and therefore it is soluble in our ammonia and water solution. So that's what we did today. We made three complex ions, right? The ones that were so fun to name. Those are our complex ions. So here's kind of what happens. So here's that silver chloride. That's a, oops. Here's a silver chloride. That's a solid here. And then it's insoluble. But then we add our ammonia and all of a sudden we make these complex ions. And this makes or increases the solubility. And we're going to talk about these ligands and stuff when we get to complex ions and transition metals. Probably November, we'll talk more about these. Now, solubility of metal hydroxide. So we do this one in lab too. This one's actually really fun. And we talked about this a tiny bit last time. So many metal hydroxides are insoluble, right? So if we looked at a solubility table, they're almost all insoluble. But they become more soluble in acidic solutions because if we remove the OH, so we talked about this last time, when we remove the OH, so if we add acid, it reacts with the OH, removing the OH from the solution, which increases the solubility. So it's just Le-Chat liase. But some metals also become more soluble in basic solutions. And in this case, they end up acting like Lewis bases. This is called amphoteric. Amphoteric just means that it can act as an acid or a base. So we talked about water being amphoteric at the very beginning of the semester, where water can act either as an acid or a base. Well, we've got some other substances that can act as either acids or bases. And so these are the ones we've actually seen this happen in lab. I don't know if lead was amphoteric in lab, but a lot of these were. And this is why you had to like make sure it was pH neutral or not pH neutral. So let's look at aluminum because we actually do this one in lab. So when we put aluminum in water, it's hydrated. So it means you've got like aluminum and then you've got these, this is water, OHH, right? So it's got all these waters that are just surrounding it. Right. And so that's what it actually looks like when it's in water. All the negative, partially negatives are attracted to this aluminum here. And when we add OH, it drives the equilibrium to the right. Because again, what happens is the OH reacts with this, which then decreases it. And Le-Chat liase, if this decreases, like our buckets, we take this one out, it goes to the right, which I can never figure out if I'm mirrored or not, if you can see what I can see correctly or the same way. It's going to go to the right because it removes the OH molecules. And so when we do this, it becomes more basic, sorry, it becomes more soluble in a base also. So some compounds like aluminum are insoluble at a neutral pH, but they're soluble in both acidic and basic solutions. And I'm going to show you these complex ions and how they look like. So here it is, oops. Here's an acidic solution, and there's that aluminum surrounded by the waters. And so you can see it's aqueous, soluble. But pH neutral, we get this, right? So this is what we made today, but we just take out the water. See, look, if you take out the waters, it ends up being this aluminum hydroxide. That's what we made today at pH neutral. But if it's basic, it makes this complex ion, which is again, aqueous. And so that's why in lab, you always are checking with it. It's like, oh, make sure this is basic, make sure this is pH neutral, because some of these metals and these hydroxides have different solubilities depending on the pH. And we call this amphoteric. So amphoteric hydroxides, meaning they can act as either acids or bases depending on the situation. Okay, so that is the end of that section.